So now I want to calculate the logical effort of this guy. So we'll first do the pull-up logical effort. Okay. So we'll do pull-up. What is the, the load capacitor is being charged up through a PMOS transistor of size 2/3. So I first need to construct my reference static CMOS inverter of same drive strength. Remember that, right? Now I'm going to refine my definition. I'm not going to say same drive strength that can provide the same current to the load capacitor for charging or discharging. Drive strength is slightly vague. You might think it's a resistance. But because of the pseudo-PEM NMOS problem where I have currents from the PMOS also, I'm going to change the logical effort definition slightly to say is ratio of gate capacitance compared to a static CMOS inverter which can provide the same current to the load capacitance for charging or discharging. Okay. So therefore here my reference inverter is the following. This is 2/3. Therefore, I'll make this 2/3. Now, if that is 2/3, what should the NMOS size be? 1/3. So, this total capacitance is equal to how much? CA. This is input A. CA is equal to how much? C. What about here? CA equals input is connected only to the NMOS transistor. So 4/3 C. Therefore, logical effort pull up is equal to how much? 4/3. Correct? Note this is greater than 1. It's an inverter. This is just an inverter. Logical effort for pull up has gone up 4/3, basically because we have brought the pull ups, the drive strength, we have brought it down. We have made this 2/3, and that's why this inverter has lower drive strength. Okay. So here there is no confusion because when the output is being pulled up, it means my input fell instantaneously, and therefore the NMOS turned off. So all the current that is coming from the supply is flowing through like this. And therefore I said, I can interchangeably talk about resistance and current here because the same current is flowing through the load capacitor, no problem. So therefore that 2/3 I replicated here, constructed the NMOS size and got the logical effort as 4/3. Now, what about the pull down logical effort? This is 4/3, 2/3, output Y. I am going to construct my reference inverter. Okay. Now, question is, this is 4/3. Can I put the 4/3 here? Can I make this 4/3? If this is 4/3, what should the PMOS be? 8/3. What's the logical effort? Yeah? So, CA here is 4/3 times C. What about CA here? It is 12/3 into C, that is equal to 4C. So, is the logical effort 1/3? Again, go back to how we constructed the unit inverter. Question is not whether the resistance is equal. How much current is available to the load capacitor for discharge is what matters. So here in the pseudo NMOS case, what matters is this current. So input is going instantaneously high. Therefore, we know that the current coming out of this load capacitor should be I. So what you should do is not this, but instead take this I and put the number here. What is the number I should put if I want I? 1. If this is 1, what is PMOS? 2. Therefore, this will be how much? CA will be 3C, which implies logical effort of pull down equal to 4 by 9. Which is less than 1. Much less than 1, it's close to half. So, just to make sure that we have been consistently doing all our things correctly, you go back here, right? For example, let me go back and let me take the high skew inverter, for example. Or let me take a low skew inverter. This is 1 and this is 1. This is a low skew inverter. So in order to find the logical effort, what did we do? We first constructed the reference inverter. And how did we construct that? This is for, let's say I wanted to do it for pull down. I needed to construct the reference inverter such that the NMOS transistor had the same drive strength. So I said this you can put here, right? And therefore this will give you 2. And then we calculated the logical effort, right? But this is equivalent to saying that the current to this guy is actually I. Because when my input goes high instantaneously, the NMOS turns on and the PMOS cuts off. So all the current coming out of the load capacitor is flowing through the NMOS. Implicitly what we were doing is actually saying that if this is I, then this is what I am going to put here as a size. So that the current through that NMOS transistor is still I and therefore that is also 1. And then you say that this is 2. Then the logical effort is basically, just 2 by 3 or something like that. So what we have been doing till now is perfectly consistent with what I am telling you now for the pseudo NMOS case, because all the current from the load went through the NMOS or all the current from the PMOS went into the load. There was no current splitting there. So in the pseudo NMOS case, you only have to make sure that this current is what I have to find. I have to construct my static CMOS reference inverter to have the same drive current I as my reference, as the pseudo NMOS inverter here. And therefore the reference inverter size is going to be 1 and 2. Clear? Yeah. Yes. That's exactly what it was. But if you take the, you should be careful. When I take the pseudo, let me take this high skew inverter or low skew inverter. When I wanted to, this was basically for pull down. When I wanted pull up, what do I do? Then I have to take the PMOS 1, then become 1.5. So that will change. Yeah. 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 No, I didn't understand. Yeah. Yeah. No, that's what I said. So okay, good question. Let's rework out this pull up case, right? For my pseudo NMOS. NMOS pull up. Okay. A, this is my load capacitor, CL. What is the definition of pull up? Ideally, my input falls and turns off my NMOS transistor instantaneously. Correct? So therefore, so if this is 4 by 3 and this is 2 by 3, I have a current IP which is equal to I by 3. Correct? Now IP and then there is a load current IL. Now because the NMOS is cut off completely, IL equal to IP. Therefore, when I now constructed my reference inverter, what do I say? This is equal to I by 3. I am saying this value has to appear here. It must be compared to a reference static CMOS inverter such that the PMOS transistor provides a current of I by 3. How will you get I by 3 if the size is 2 by 3? And therefore, if that's 2 by 3, this has to be 1 by 3. Yeah. No. For a PMOS, the current is, if a PMOS transistor has a size alpha, W is alpha, then the current to that is alpha I by 2. Where I is basically with the current of a NMOS transistor, you're right. Yeah, I is always this, remember, don't forget that. It is basically a unit NMOS transistor discharging a capacitor CL from VDD to VDD by 2. That current is I. So for that, if I want the same current I in the PMOS, I have to make it twice the width. Clear? So it's very important to recognize that we have not been doing anything wrong or inconsistent. It's just that I could interchangeably talk about resistance and current because there was no, other current there. In pseudo NMOS, I cannot do that. I have to do it very carefully. Clear? Any other questions? Okay. So now I can, take this logic further and say, okay, if I want let's say I want a NAND, okay, NAND 2 gate in pseudo NMOS. Okay. So what do? I basically need to add another transistor B. This is 2 by 3. What should the size of the NMOS transistors be? Inverter was 4 by 3. It should be, sorry, 8 by 3. See, now I can combine resistances because two transistors are in series, right? The same current is flowing through both of them. So this has to be simply 8 by 3 and 8 by 3. Okay. Now, what is the pull-up logical effort of this guy? What is pull-up logical effort? CA equal to CB, capacitance on the inputs. What are they? What is the capacitance first? 8 by 3 times C. Correct? So what is the pull-up logical effort? So how do you do that? So again you have to construct the reference inverter, right? For pull up, pull down. So pull up static CMOS inverter is like this. What should the PMOS size be? 2 by 3. NMOS therefore is 1 by 3. Therefore, the pull-up logical effort is how much? 8 by 3. Clear? What about pull down? I got to construct my reference inverter again. What should the NMOS size be? 1. Because even here, the effective current that's going to come out of my load is going to be I. This current to the NMOS will be 4 by 3 times I. And this is going to be I by 3. Therefore, I am going to take this current and put it as my NMOS transistors with 1 and 2. Therefore, pull down logical effort is how much? 8 by 9. Clear? So you have to, it will turn out that these reference inverters don't change. Because from now I am going to size my transistors so that the effective drive strength is the same with respect to the unit gate. So these reference inverters will remain the same whether you do NAND, NOR, whatever stack. Okay. So now try this. NOR 3 gate. Can you first draw a pseudo NMOS NOR 3 gate? A, B, C, output Y. What should the PMOS size be? 2 by 3. NMOS? 4 by 3. 4 by 3. This also will be 4 by 3. What's the pull-up logical effort? 4 by pull down logical effort. 4 by 9. What if I made this an N input NOR gate? It's the same thing. That is the key advantage of getting rid of your PMOS stack. For the NOR gates, where the logical effort grows because my PMOS stack size is growing, I am able to make sure that the logical effort is 4 by 9 irrespective of how many ever input NOR gate I have. Okay? Clear? Yeah. Doubt? Why is the PMOS 2 by 3? Because we just calculated based on the noise margin, right? VOL has to be something, and I said, okay, let's assume that WP by WN has to be half. It gave us a good noise margin, so I said that's 2 by 3. So this PMOS because it's just one PMOS pulling up. That's 2 by 3 always. See, the worst case is 2 by 3 pull up and one of the 4 by 3 is pulling down. So therefore it has to be 2 by 3 and 4 by 3 as we say. Okay? Clear? I know this is like, it takes some time to sink in, settle in. So please think about it. Go back, work out this example. So in fact, I would suggest that you should necessarily go back and work out this whole table here. Okay, I'll put this in the tutorial as well. This here, right? For a NAND 2, for a NOR 2, work out these things. You should get these numbers correctly. Okay. Clear? Now parasitic delay is what? You just, again, you're going to count diffusion capacitance divided by the diffusion of that reference static CMOS inverter that we constructed. So work this out as well. We can discuss it in a tutorial session later. Clear? Okay. I have 10 minutes to go. So now clearly this is not a gate that can be used because I have a static current when the input is high and the output is low. Right? I have a standard, I mean a DC current, right? And that's going to kill your power. So it can't be used in reality, right? So therefore something has to be done to exploit this fact that we are getting rid of the PMOS stack, but at the same time we are able to, you know, get this benefit of lower logical effort. So how do you do that? It turns out it can be done with cascode voltage switch logic. So let's look at a simple inverter. A, right? Normally, I would have connected this to ground if I wanted a pseudo NMOS inverter. Now I want to do something slightly different to overcome that static current problem. A bar, okay, and I'm going to cross couple it like this. Okay, so let's first analyze the static cases. A equal to 0, right? Let me use blue for that. This is 0 and this is 1, VDD. Correct? Now if input A is 0, let me also label the transistors so that this is N1, P1, N2, P2. If A is 0, input N1, I mean transistor N1 is turned off, right? Now on the other hand, right, so assume that the sizing is very similar, right? You have 4 by 3, 2 by 3, 4 by 3, 2 by 3, okay? On the other hand, if A bar is 1, I am assuming now that the input and its complement is available. A and A bar are available together, okay? Which is true in some cases and therefore you can use it in those special cases, okay? So if A bar is 1, then what happens? The N2, P2 will now start fighting, right? And the output, let me call this Y bar and Y. The output Y is going to come somewhere near VOL, right? Somewhere, so it's a very low value. Now if output goes to VOL, then the VGS of P1 will now become how much? What? VOL minus VDD. Again, it will be approximately minus VDD. It will turn on P1 very strongly. And therefore, Y bar will get pulled to VDD. Now if Y bar goes to VDD and the gate of P2 is connected to Y bar, then P2 will now turn off. Therefore, P2 will cut off. So we are using this cross coupling to turn off the other transistor. So this is clearly a case where it's like a pseudo NMOS transistor, logical effort is low. Note very importantly, my input A or A bar is still connected only to the NMOS transistor. They are not connected to that cross coupled stack anywhere. If it is connected, then the logical effort will go up. That's a problem, right? So this cross coupling is happening only between output and this. Of course, the delay might be slightly different because of this cross coupling, but to a first order, I still maintain the same logical effort, but eliminate this problem of static current flow. Similarly, if I now do the case where A equal to 1 and this is equal to 0, exactly the opposite arguments will come in, and the P1 will get cut off by Y. Correct? So how do I take this logic and generalize it to any implementation, right? Suppose I want to do a NOR or a NAND, right? So it's very simple. All you have to do is I'm going to look at a NAND 2 gate. So normally my pseudo NMOS implementation would be like this. This is a NAND 2, A, B. What should I implement on the other side? Yeah? B? No, I can't hear you. AB? Exactly, right? It's not just AB in parallel, it is actually the A bar, B bar. What is this logic here? This is A into B, right? Whole bar, because it's connected to ground. What is this logic? It is A bar plus B bar whole bar, which is equal to AB. So you implement true logic on one side and the complement logic on the other side, then you will be guaranteed that one of these stacks will be turned off always, right? And this cross coupling will take effect and it will cut off the other guy very easily. Okay, so in general, you got to implement this. You implement the function f here, then you implement the function f bar here, and the inputs are connected to these guys. A1, A2, AN, A1 bar, A2 bar, AN bar. So you can implement any arbitrary logic in a similar to pseudo NMOS style, but avoid all this static current. Of course, the key assumption we are making is both input and its complements are available out here. I am not generating, for example, if I have to generate A bar internally, then this is not useful, because then the logical effort will change. You have to calculate what that capacitance is, right? There is now a fan out. A is driving this gate plus the inverter. So that's not useful. A and A bar should be available from outside simultaneously. Okay, for example, if you are trying to implement a decoder, typically you will find that you have A and A bar easily available. Okay, now so when the decoder output is being used somewhere, since both output and complement are available, you can just feed it to a CVSL logic at some point.